Hi everyone, this is Sir Amboy and welcome to my YouTube channel. So, in the previous topic, we have learned how to solve simple differential equations and some initial value problems. And now, in this topic, we will learn how to formulate differential equations that would serve as mathematical models, which would then enable us to make predictions or understand the behavior of a physical system or a certain natural phenomenon. Now, to give you an introduction to the modeling process, let us proceed to the next slide. Perhaps the most important application of differential equations is in modeling various physical and natural phenomena. An engineering problem can be solved first by formulating a mathematical representation called a model. And the process of setting up a model, solving it mathematically, and interpreting the result is called modeling. So, what then is a mathematical model? A mathematical model is an expression involving variables, functions, or equations that represents a real-world phenomenon. So you might ask, why is there a need for us to create mathematical models? The purpose of a model is to understand a certain phenomenon and to make predictions about the future behavior or outcomes of a system, event, or quantity. For example, you want to model the COVID-19 outbreak, and you want to make predictions about the number of individuals who will be infected after 1, 2, or 3 months. Now, to illustrate how the modeling process is done, here is an illustration. First, there is a real-world problem that needs to be addressed. The next step is to formulate a mathematical model which would be in the form of a differential equation. And how can this model be formulated? First, variables must be assigned to the quantities involved in the modeling process. For example, if you want to model a population and predict how it grows with time, then our variables could be P for population and T for time. Now, after the variables have been assigned, the next step is to establish the relationship between the variables involved in the modeling process. After the variables have been assigned, the next step is to establish a relationship between the variables to come up with a mathematical model, which for our purpose is a differential equation. And this can be done through the application of some existing physical laws. For example, Newton's law of motion, or if there is an electric circuit involved, we can use Kirchhoff's voltage law or Kirchhoff's current law. So these are just some of the few laws which we can use. And of course, there are many more others. Now, if there is no existing law applicable, then a sufficient amount of data is necessary to establish a trend or to establish the relationship between the quantities involved. Once the differential equation has been formulated, its solution can now be obtained using the known methods of obtaining the solutions of various differential equations. So it can be solved analytically or, for most practical applications, numerically using computer software. Now, the solution to a differential equation represents the mathematical conclusion which can then be interpreted to make some real-world predictions. Again, for example, a model of the COVID-19 outbreak has been developed by scientists and researchers. Now, using that model, we can make interpretations and predict how many individuals will most probably be infected after 2 or 3 months. Of course, with some conditions and restrictions applied. However, a model is normally tested after the result has been obtained. Why? This is to establish an accurate model. If the initial result or prediction does not match the actual data, then the modeling process has to be checked for some errors in order to obtain more accurate results. So now in the succeeding examples, we will only formulate the differential equation that models the given problem. And finding the solution of these equations will be reserved for some other topics later. For example, in Module 3 or in Module 5 of this course. So let us now solve some practical examples. Example number 1 is about radioactive decay. So here's the problem. Experiments show that at each instant a radioactive substance decomposes, the rate of decomposition is proportional to the amount of substance present. So if we are given a certain initial amount of a radioactive substance, formulate a differential equation that gives the amount of substance present at any time later. Okay, so I will demonstrate how to obtain the differential equation for this particular problem. Okay, and to illustrate the modeling process, I will discuss the steps one by one. First, we need to assign or define the variables that we will be using for the mathematical model. So here, the quantity that is involved is the amount of radioactive substance. So the differential equation that we should be formulating should give us the amount of the substance at any given time. Okay, so we need to represent that amount of substance using a variable. For example, I'll be using the variable y to represent the amount of substance present at any given time. At any given time. Okay, it's also said that there is a certain initial amount of substance given. So, if that is an initial amount, I will use the subscript O. So, this YO is the initial amount of substance. And since the substance involved is radioactive, it decomposes with time, meaning the amount of the material sample decreases. That means that with time, this Y decreases. And according to the problem, the rate of decomposition is proportional to the amount of substance present. Now, we are ready to do the next step. After having defined the variables, of course, here, time will be represented as T. And the amount of substance Y decreases with time. Now, how are we going to establish the relationship between the amount of substance and the time? It is actually stated already in the problem. The rate of decomposition is proportional to the amount of substance present. If the substance decomposes, the value of Y decreases with time. And the rate at which it decomposes can be represented as a derivative. Why? Because in calculus, the word rate of change is synonymous to the word derivative. So if the amount of substance at any time is Y, and this substance decomposes or decreases with time, then how fast does it decompose? The rate at which the material decomposes or the rate at which the substance decreases can be written as dy over dt. And according to the problem, this rate of decomposition is proportional to the amount present. And the amount present is y. So we can represent this worded expression, the rate of decomposition being proportional to the amount of substance present, as dy over dt is proportional to the amount of substance y. The next step is for us to formulate a working equation. Okay, so from this proportionality relationship, we can come up with an equation. So, in order to make an equation, we need to remove the proportionality sign and instead use an equal sign. But I have to introduce a certain proportionality constant k. So, this is a proportionality constant, and in this case, this is called the decay constant. So, this constant has something to do with the rate at which the material decomposes. And another important thing, since the amount of substance decreases with time because it decomposes, we need to add a negative sign here. Meaning that this quantity, the quantity y, decreases with time. So, this is now the differential equation that describes the amount of substance. So, if we solve this differential equation, we would be able to determine the amount of substance present at any given time. But at the moment, we will not be solving this differential equation. Our goal in this topic is to formulate a differential equation that describes a certain real-world phenomenon or a certain real-world problem just like this. Okay, so I hope that is clear enough. Now, let me give you some more information about radioactive decay. So, when is a substance radioactive? A radioactive substance has its nucleus, or the nucleus of the atoms is very heavy. And because it's heavy, it is unstable. Now, the nucleus, which is unstable, emits particles and radiation. So, there are three types of radioactive decay. So, it could be an alpha decay, or a beta decay, or a gamma decay. So these are the particles or radiation involved in the radioactive decay of a substance. Now, an important application of radioactivity is in the determination of the age of artifacts found or unearthed by archaeologists. So researchers are using what you call the radioactive carbon dating technique in order to estimate the period of time in which a certain, for example, dinosaur lived. Of course, that's hundreds of millions of years ago. So, and they are using the radioactive element carbon-14. Now, let us move to the next example. Example number 2. Here, we have a freely falling body. So, an object is falling under the influence of gravity. And as it falls downward, it is subject to air resistance that creates an upward force that is proportional to the velocity of the object. Now, obtain the differential equation that describes the velocity and the position of the object at any time. Assume that the mass and the acceleration due to gravity are constant. So, assuming that the object we are talking about is an apple. So, as it falls towards the ground under the influence of gravity, it is also subject to air resistance. So, this is the more realistic situation because in reality, there is air resistance that opposes the motion of an object as it falls towards the ground. Now, in many experiments, it has been found out that the force due to air resistance is proportional to the velocity of the object. So let us now indicate in this illustration the forces acting on this object as it falls towards the ground. First, we have the force of gravity, which is represented by the weight of the object, mg. But aside from the weight, so there is a force due to air resistance. So if the motion is downward, the opposing force, of course, is upward. And according to the problem, that force is proportional to the velocity of the object. So we have here the proportionality constant K. And in this K is called the drag coefficient. So now, we have the free body diagram already. What is the next step? The next step is to formulate the differential equation that describes the velocity of the object at any given time. So here, the quantity that we would like to describe is the velocity of the object as represented by the variable v. So, how are we going to come up with such an equation or a differential equation? So, unlike in the previous problem in which the differential equation has been formulated from the actual statement given in the problem, because it has been mentioned in the problem that the rate of decomposition is proportional to the amount present. But in this problem, no such rule is mentioned or stated. That is why we need to apply a relevant physical law. So, since we have a body that is moving and accelerating due to gravity, we can apply Newton's law of acceleration, okay, or Newton's second law of motion. The net force acting on a body is equal to the product of its mass and acceleration. So this is where our differential equation will be coming from, okay? From this equation, Newton's second law of motion, we will formulate our differential equation. Now, the net force acting on this object can be obtained by getting the sum or the resultant of these two. So we have mg minus kv is equal to m times the acceleration. So you might wonder why the sign of mg is downward and the sign of kb is negative, while in fact the arrow is pointing upwards. So since the motion of the object is naturally downward, so by convention, we make it positive. And since this force is opposing, we make it negative. So this is actually proportional to the velocity and is in the opposite direction. Okay? Proportional to the velocity but is in the opposite direction. That's why its sign is now negative. Okay, so here our variable is v. Okay, but we have the quantity acceleration. Okay, so in order to create a differential equation, we need to establish a relationship between the acceleration and the velocity. And we all know that the acceleration and the velocity are related by this kinematic differential equation, that the acceleration is the rate of change in the velocity. So therefore, I can replace this a with dv over dt. So now, let me rewrite the differential equation. We have mg minus kv equals m times dv over dt. Okay, so we now have the differential equation whose dependent variable is v, and this v is the velocity of the object. Okay, so now this differential equation is the model that describes the velocity of the falling object. If we can solve this differential equation, then we can determine the velocity of this object at any given time. At the moment, we will not be solving for this differential equation. The solution to this differential equation will be solved in Module 3. For the meantime, it is enough that we are able to establish a differential equation that models this particular situation. Okay, we can actually rewrite the differential equation in terms of the standard form. So we can divide both sides by m and transpose this term on the other side. Okay, so we have dv over dt plus k over mv equals mg. Okay, oh, we divided both sides by m, so this will now be simply g. Okay, so this is not the differential equation that we are looking for, but it only describes the velocity of the object. But the question says that we need to obtain also a differential equation that describes the position of the object at any given time. Therefore, we need to formulate another differential equation, this time describing the position. So, since the motion is in vertical translation, we will let y be the variable that represents the position of the object at any given time. Now, how is the position related to the velocity? So we know that the velocity is the rate of change in the position of a body. And because of that, I can replace this v with dy over dt. So since we are getting the derivative of a derivative, we can write it using the second derivative. Okay, so I can now rewrite the differential equation d squared y over dt squared plus k over m times v is dy over dt, and then equals g. So this is now the differential equation that describes the position of this object at any given time. So this is a second order differential equation which is also linear at the same time. So this is a first order differential equation which is also linear. So we will solve this differential equation in module 3, and we will solve this differential equation in module 4. Again, at the moment, it is enough that we know how to formulate differential equations. Now let us solve the third and last example for this lecture. So here, we have an RL circuit. What is an RL circuit? This is a circuit containing a resistor and an inductor. So we have a series RL circuit connected to a voltage source. So the voltage source is denoted by V. So develop a model of the circuit that describes the current at any time t greater than 0. So here is the illustration for the circuit. So this is the voltage source represented by V. So here we have the resistance R, and here we have the inductor L. And of course, there is a current flowing through the circuit represented by the variable I. Now our goal is to develop a model. So that model is a differential equation describing the current at any given time. Okay, so how are we going to formulate the differential equation? First, we need to set up the variable, but the variable is already given here. The variable to be used is I, and the independent variable is time. How are we going to come up with a working equation? So we can apply another physical law. What physical law is appropriate to be used for this circuit? So we can come up with a differential equation. So we can use KVL, or the Kirchhoff's voltage law. So if you're not familiar with KVL, KVL states that the summation of all the voltage drops in a closed path or a closed loop is equal to 0. I repeat, KVL, or Kirchhoff's voltage law, states that the summation of all the voltage drops in a closed path is equal to 0. So here, the voltage is V, and of course, there is a voltage drop in the resistor, and there is also a voltage drop in the inductor. Now, according to KVL, if we add all the voltage drops in this closed path or a loop in electric circuit, the answer should be 0. Okay? So now let us formulate the differential equation. So here, the voltage is V, and then minus. So here, the voltage drop, of course, is the product of the current and the resistance. V is equal to IR, according to Ohm's law, right? Okay, so that is I times R. How about the voltage drop in an inductor? In an inductor, the voltage drop, VL, is equal to L, the inductance, times DI over dt. Okay, so take note of this. If you are not yet familiar, then I now give you the relationship between the voltage source in an voltage drop in an inductor and the current through it. So the voltage drop in an inductor is proportional to the rate of change of the current. So the constant of proportionality is the inductance of this inductor. Okay, so we put here in the equation the voltage drop for the inductor, which is L times di over dt. And of course, this is equal to 0 according to KVL. Okay, so we now have a differential equation. So I can transpose these two terms on the other side and equate it to V. So L di over dt plus R times I equals V. In writing the differential equation, it is a convention that the first term has a coefficient of 1. Okay, so we need to divide both sides by L. So dividing both sides by L, we will get di over dt plus R over L times I equals V over L. Okay, so this is now the differential equation that we are looking for. Okay, so this is the differential equation that describes the current in this series circuit at any given time. So we will solve this differential equation in module 3. So if ever you'd encounter a problem that involves a capacitor, so the voltage drop across a capacitor is equal to Q over C. So Q is the charge stored in the capacitor and C, of course, is the capacitance. So again, if you ever encounter a problem that involves a capacitor, this is the voltage across a capacitor. It's the charge divided by the capacitance. So that would be all for this topic. Bye!